So, hello everyone. I hope you're all having a good day. I hope you're in a nice food coma after the lunch. Sorry about the clickbait title. You've got to stand out in the selection process somehow. This is how I compensate for lack of skill. Who am I? I'm not going to bore you because you don't really care. I'm basically the wish.com version of the guy in the other room. So, you don't care. I'm not famous. You can find me at all these places if you're interested. I do the activity pubs. I do all of the stuff. For those of you who don't actually like going to conferences, everything's online now, so you can skip ahead, go get a coffee. I'm not going to judge you. It's all there. Or go to the other room. It's fine. All of the slides are there. Feel free to go straight through. Speaker notes, just press S. It's all there. Go nuts. I see people taking photos, so I'll just hold off for a second. Beauty. If you haven't got it, too late now. So my hobby is building search engines, and up here are some of the things that go into it. And when I say some, I mean just some. The list is endless when it comes to this sort of stuff. And every part that you see there is one of those problems that you lightly scratch and you discover that there's people getting PhDs in it. So it constantly keeps me engaged and learning. And I just have a wonderful time playing with algorithms and stuff that go into it. It's better than writing the n to the power of 6 quadratic function that I did that, I can reduce the lines to solve some sort of a problem. So it's quite fun. And a few years ago, I was working on a new index for searchcode.com, which is one of my search engines that I work on from scratch. Now, this runs on a dedicated server. I know, heresy at a serverless function. And I mentioned this to a work colleague when I was doing it, and he said, why don't you deploy it in AWS? Because, everything that we work with generally is in AWS. And I responded that it's prohibitively expensive. Like for the server that I've got here compared to what you have to pay on Amazon, like the price is just ridiculous. And you need a lot of persistent storage, you need a lot of RAM to pull this off. And then he kind of mentioned, why don't you use AWS Lambda? And at the time I responded, the lack of persistence is a problem. So Lambda or any other serverless function, they work really well for certain classes of problems. So if you can rebuild the state similar to the way they used to do PHP back in the day or even now, or if you're responding to events, they work really well. Great for that. Absolutely fantastic. The lack of persistence is an issue in search because you either store the index in RAM or if you're old school, store it on disk. So I was explaining this to him. And then I think halfway through, I must have looked like I had a stroke or something. I just trailed off. Something occurred to me because there's a very famous saying in computing. Never do at runtime what you can do at compile time. And I decided to see how far can you take this idea. So I'm going to use AWS Lambda to build a search engine. Now, why AWS? 2 reasons. A, I'm most familiar with it. And B, AWS isn't running a search engine like Google or Microsoft Cloud, so they're less likely to shut me down. So the idea, some see constraints, I see free compute. So how do we get around the lack of persistence? So what we're going to do is we're going to bake the index into the Lambda itself. In other words, we're going to generate code which contains the index and then compile that into the Lambda. We're going to do it at compile time. The plan is then we shard across individual lambdas. So each one holds a portion of the index, and then we deploy the whole thing. Now, the great thing about this is 100% serverless. As a matter of fact, with 75 gig of space, we're probably going to slide into the free storage tier and not have to pay anything unless people are using it. Now, that sounds insane, but this is actually a massive advantage when it comes to search engines because search engine, you need big, powerful clusters of machines, but if nobody's using them, you're paying for all of this dedicated compute that nobody's using. It costs a fortune. This, nothing. So I set out to prove the theory. Now, I started with a simple brute force search. Now, this sounds like a stupid idea, but brute force is a viable strategy, assuming that you've got a lot of force. We all know tools like grep, ripgrep, they can walk through gigabytes of content in seconds, right? So this isn't a bad idea in theory. So I created 100,000 strings. I think they were actually longer than this at the time. And I ran this locally, and it returns in like 100 milliseconds because, CPUs are extremely fast. And then I wrote a simple one that's doing the same thing, the search, and I deployed it to Lambda. This doesn't work. I underestimated how weak the CPUs in Lambda are. Searches were returning in like seconds, they had like 5, 10. It was really awful. And even when I bumped the RAM to increase the CPU allotment, didn't really help. I tried multi-threading with that RAM. No. So backup plan. Okay, we're going to embed an index into the Lambda, allowing for a quick scan of the documents, and then we can just process those. So The definition of an index is a little fuzzy. I'm effectively defining it as a function that I pass in some terms or a term, and it returns a list of integers which refer to documents that are likely to contain those terms. Okay, and then I can do whatever it is I need to do to search that. So here's a textbook 101 index. It's just a map or a dictionary, strings to ID. So serverless and days, those two terms, they're found in documents 3 and 1337. Brimful Asher is found in 45. I'm glad somebody got that. This is not compressed. So walking those lists for common terms can take a long time. And as I said, it's not compressed. So the next thing we've got to do is we've got to compress the list. So you end up using a thing called Elias Fano. I'm not going to go through how it works. It's not the easiest thing in the world, but it's not too bad. And you have a data structure that's called a skip list. So you can jump through the list quickly. So this saves us in memory, allows us to process it. Because we're putting the index into a Lambda, we really want that compression, and because Lambdas are weak, we really want the performance, okay? I did attempt to create a compressed skip list, and I got 2 turkeys, not the eagle that I wanted. So I started rethinking the approach. Now, I had the same problem with searchcode.com, and I had solved it over there using Bloom filters. And you see, there's a technique to search using Bloom filters, but it kind of helps if you know what a Bloom filter is first. Anybody know what a Bloom filter is? Great, you're all about to learn what a Bloom filter is, and those who already know, you're going to learn again. So what is a Bloom filter? So it's a space-efficient, probabilistic data structure that you can add terms to and check if the term was added. They never return a false negative. So if you didn't add it, and they do, but they do occasionally lie and report that something is added when it wasn't. So they lie to you and say, yeah, you added this, but when you never did. So here's an example of a Bloom filter. It's a 16-bit Bloom filter. It's just a slice of booleans or an array of booleans. By default, all set to false, represented by 0 in this case. So to add something to the Bloom filter, we get whatever it is that we're adding, and we hash it multiple times using an integer hash like FNV, FNV1, one of those. And then we use the resulting outputs to map to bit positions inside our filter, and we set them to true. So we've now added big. We're going to add another term. So same process, hash 3 times, set the bits, we're all good. Third term. You'll notice in this case 2 of the bits overlap. This is an expected property of the Bloom filter. This is how they're space efficient by reusing the bits, okay? So this is nice and good. This is expected property of the Bloom filter. So now we want to check, did something get added to it? So we roughly do the same thing. We get the term, we hash it 3 times, and then instead of flipping the bits, we just probe them. And in this case, we can see that all those bit positions are set to true. So we can say big was probably added to this Bloom filter. Now we'll get to why it's probably in a second. Another check. Now you'll notice that the middle bit is 0. So that means we know Sydney was never added to this filter, okay? This is great, fantastic. Now we get to the false positive. So in this particular case, we've hashed and all of the bit positions are true, but we never added this term. The bits were supplied by others. So you'll see that there's a lot of tweaking when it comes to Bloom filters to reduce this false positive rate, either by making the filters bigger or tweaking the number of hashes. So how do you do a search with this? So the trick is you just add more Bloom filters. And you can't see this, unfortunately, because it's a bit cut off. This would be 4 Bloom filters. They're all 8-bit Bloom filters in this particular case. So to search, we just loop over each one of the Bloom filters, probe the bit positions, and if we get all 1s, then we've got a match. If we see a 0, we haven't got a match. In this particular case, you should be seeing that the last one match, which is document 4. So they've got a lot of advantages going for them, Bloom filters. They're compressed by nature, as we covered, because they're reusing the bits, so they're only using a few bits per term added. Adding is really simple. You just add a new filter. And searching is just a really simple for loop. You can hand it over to your cousin to write. There's problems with them, though. So firstly, there's an 8x overhead when it comes to using booleans. Now, the reason for this is when you write a bool in your code, it's actually stored using a byte in memory. So, and this exacerbates the second problem, which is this search is unbelievably slow. And this comes down to effectively how RAM works when it comes to pulling bits out of memory. So when you probe a single bit on most modern systems, it actually pulls back 512 bits from memory. And this is because when you get down to the CPU, it's reading a whole cache line. So it's 512 overhead to probe a single bit. So On average, you end up walking all the memory for your filter, depending on which bits you probe and depending on how big it is. And this is one of the reasons this approach for search fell out of favour in the 70s, because you sort of end up walking all the addressable memory. Here's an illustration of the problem. So this is a 2048-bit filter. Don't count the squares. I can assure you there is that many. Each square is representing a bit. We've hashed our terms to match 6 bit positions, and we've used a good hash function, which has given us a nice spread, good distribution. So we probe those bits. And because all the bits are within 512 bits of each other, we're likely to pull the whole filter across the CPU. Now, this doesn't sound so bad. You're like, RAM is fast, right? RAM actually isn't as fast as you think. Modern CPUs can theoretically do, 100, 400 gigabytes across the CPU of RAM access per second. In practice, you're more likely to get 20 or 50, and it goes down from there based on what you're doing. Can we do better? In 2017, in SIGIR, this paper about Bitfunnel was released, and it described how Bing.com, yes, Bing, the search engine, uses bit signatures or Bloom filters to power its fresh index. And I think it actually powers the whole index now. It won Best Paper at the conference, which is probably one of the most prestigious IR conferences in the world. What got my attention is it's got Dan Liu as one of the authors. Anything he does I pay attention to. Good enough for Dan Liu, good enough for you. He's got a great blog, by the way. You should go read it. So in the 80s, there was this smart guy called Roberts, and he noticed that you could rotate the Bloom filter, assuming each filter's of the same length. So you do that by turning rows into columns. So each row used to represent a document. Now each column is. So we're building on this. So now we want to do the same query that we did before, previous search. So we're searching bit positions 1 and 7, which are now rows 1 and 7. And we grab those 2 rows. Then what we do is we do a logical AND between them. Now, this is great. Logical ANDs in the CPU are as close to free from a performance point of view as you get, okay? All of the time for this sort of operation is dominated by memory lookups. In this particular case, we've ANDed. So you'll see that there's a singular 1 left at the beginning. Remember, we mapped our documents right to left. That corresponds to document 4. Exactly the same role as our other Bloom filter, but far less memory access. Now, the result of this is it reduces the memory access by like 200 times, assuming you've got a big enough Bloom filter, which, guess what? We're about to. So here's a 64 document, 16-bit Bloom filter. Remember, the bits are represented down, and it's 64 because I'm using a 64-bit integer. So it's completely empty, 1 for each document, each row, and then we're going to go and add some documents to it. So this is what it looks like after we've sort of added 32 documents to it. So you'll notice the right-hand side is full, left-hand side is still all zeros. That's because we haven't added anything there. Now, the really good thing about this is we've optimally used the space. We haven't wasted any of the bits. So we've gone from an 8x overhead to absolutely no. And the other advantage about this is when we do the search, we're now searching 64 documents at a row. This is a massive speed up both from the logical AND, 64 documents, and all of a sudden we don't need to query everything. So how do you embed this in code? This is the brilliant part of it, and this is what made me use this for what I'm about to show you. It's that. It's literally just a slice or an array of integers, and it's really, really easy to embed. I haven't put the full example there because in practice, when I did this, it's up to 100 million of them, all after each other and then compiled into code. This is the core loop of the searching thing. Don't worry too much about it. As I said, all the slides are online. You can get it later. I find this algorithm beautifully simple. It's really good. So what this does is it loops over that Bloom filter, looking through 2,048 bits for each one of the Bloom filters, and it finds all of the interesting IDs that match the terms. And this is fast enough to run in a few milliseconds on the Lambda when I tried it. I think it's something like 3 milliseconds or thereabouts. And this cuts down the number of documents that we actually need to inspect to a manageable level. So visually, it kind of looks like this. This represents those 2048-bit Bloom filters where it's just getting the rows, logically ANDing them. If it finds nothing, it can just skip to the next one. This gets really, really fast. When it hits that failing condition of all the bits and now 0, great, we can just move on. As I said, this runs in a few milliseconds. So with that done, we now need to source the websites. Now, lists of this exist, so I just download them and filtered them to anything with .au on the end. I tried some open source crawlers, and then I ended up just writing my own custom one, locked to a single domain, which was writing all the contents out to a single format. If you are doing a crawler like this, don't overthink it. Just fake the user agent to Googlebot, and that's pretty much all you need to do. One advantage of doing this sort of thing is these lists are usually in some sort of sorted order of the most popular domains. Great, I can use that as well. So I took those orders and I used that to create a page rank inside the search. So we've now got pre-ranking as well for free. Here's an example of what the crawl kind of looks like. It's nothing too fancy. You'll notice that I threw away all the HTML. This gives something like a 50 to 100x saving on the amount of HTML of content that you need to save on the disk. This is really, really important because otherwise you end up filling up your disk really quickly. It does mean I have to recrawl if I change the format or if I want to do stuff, but you've got to recrawl pretty frequently. Cost is negligible in my case. So we had our pre-ranking with our cheap version of PageRank, but you also want to query rank. So this is when somebody types in the terms, you kind of want to rank based on those terms. Otherwise you get really, really odd results. Ranking's one of those secret sauce things that everybody talks about a lot. You know what? Just use TF-IDF or BM25. They're both really quite easy to understand. This is BM25, as you can see. It's not that many lines of code. And it works really, really well for keyword searches. Snippet extraction. So this is one of the things that I mentioned when I filled in this do a talk thing. This could be a talk on its own. It's also listed as one of the reasons Ink2Me. Does anybody remember Ink2Me? One. Really? Nobody knows? I'm very disappointed in all of you. Ink2Me was one of the original search engines. That was what powered Yahoo and a lot of other sites. They had no front end. Everybody just called their APIs. Ink2Me probably, it's attributed to PageRank. I think Ink2Me probably lost, and I think the founder of Ink2Me said the same thing. It was because they didn't extract snippets. They just showed you what they thought the website was about, but they didn't show you contextually based on what you searched on, so you had to click through. Compared to what Google did, really not that good. Not going to walk through the code. It's fairly complex. It's linked there. You can go and have a look at it. I'm really quite proud of it, actually. I base all of my, sort of string matching stuff on Pride and Prejudice, which I probably know more about than I should. The above is showing the two best matches for $10,000 a year. This is easily the most expensive part of the search, so we want to do anything we can to cut down before running this process. So it kind of looks like this. We've got our Bloom filter index that's skipping through really quickly, 3 milliseconds, and then we brute force search what's left over, and then we rank them and then sort them, pop off the top 20 results, go and get the snippets, and then return it. Beautiful. So I deployed this, and inside CloudWatch, it kind of looks like this. So we end up with sort of 140 milliseconds, and this is where somebody searched for something like the, which is not really very useful, but hey, you can do whatever you want. Otherwise, it runs in 7 milliseconds, 5 milliseconds. It's actually pretty fast. This is easily good enough to build a search engine on. Great, let's do it. So this is the design. It's an API gateway, which fronts a controller Lambda, which ends up calling multiple workers as configured by environment variables. So the workers contain the index, and when they're past the query, they do whatever parsing they need to do. They go through all that process and then return the results. The controller aggregates them all together, resorts it, and then returns it back. And then the last thing I did is I created a small HTTP server to just basically call this API, mark up the results, return it. So now we've got to build the index. So I wrote a script that walked through all of the crawled content that I've got. And what it does is it basically goes through them, it tries to stuff them into batches that once compiled and zipped would create a 50 megabyte binary. This is the goal. This is what we're aiming for. Any bigger than that, Amazon won't let you do it. When it's done, it writes out the index, the frequencies, everything else that's needed, and then it drops it on disk as content.go.1, ready to be compiled. So deployment is a simple matter of just iterating over them and building the application. Now, I originally I used the command line tools for this. A lot of people said, why are you not using CloudFormation? Has anybody ever tried deploying 1,000 binaries via CloudFormation? Yeah, it's not fun. Don't do that. It's also very against what it's supposed to do. It also makes it really hard to update them, and I would also have to upload all of those binaries into S3 and actually do the deployment. This works locally. Again, I'm trying to go pure serverless here. I'm not using S3. No storage costs for me. The last thing that we do is we update the controller to say, here's all the lambdas that you know about, and it then goes, great, I can now call them. So the result of this is I managed to get 50 million documents indexed. Now this is notable because the first version of Google only had 25 million documents. So I managed to double them using Lambdas on the free storage tier, and I'm one guy working in his spare time. How's that for technology progress? Yeah, as it says there, it definitely fits into the free storage tier. In fact, the whole thing is free if nobody's using it, so that's pretty good. So I registered a domain. I went for the most Aussie name I could think of that was available, bonzamate.com.au. Here's the UI. To make it look a little more real, I created a news feed which displays the current news articles, again, also implemented in Lambda, nice and serverless. Here's the results of the search. Now, I was going to do this live, but Wi-Fi, I'm not going to do it. You can play with it yourself. Go to bonzamate.com.au. It's there. Feel free to search. Here's the result of search based on what I knew would show the relevant news thing on the right, so it looks pretty pro. I was still feeling empty, so I parsed a Wikipedia dump for anything that's sort of vaguely related to Australia, and then I created another serverless function which I embedded that into to get the zero-click information. So you can see here it's displaying information about the submarine HMAS Onslow, which is pretty neat, I think. Makes it look definitely more professional. And lastly, a vanity search for myself because, hey, it's my search engine and my talk, I can do what I want. Those results are what I would expect, though, actually, based on Australia. Hey, talk to me later about why I don't use Google. So what is the sound of 1,000 lambdas? I don't know. It probably sounds like ching to Amazon when the free credits run out. This is the CloudWatch outputs over sort of the last 6 months. You can kind of see where I fixed some issues and rolled it out, and it's been perfectly stable and fine since then. No real problems. So conclusions. Go. Go's fantastic. Anybody using Go? Great. Remember, I'm compiling the index into the code, so we kind of need a fast compiler, which Go has. Java probably wouldn't work for this because it's got the class limits. I know you can kind of work around them, but you end up shooting yourself in the foot. Rust, I'd probably still be waiting for it to compile. Python's probably too slow for this. Bloom filters are great. People will always tell you if you suggest, oh, we should use a Bloom filter, oh, use an XOR, or use a cuckoo, or use a ribbon filter. Bloom filters are so simple and so interoperable with everything else. So they're really worth learning about, even if they're not necessarily the most efficient way. And I don't think you can actually do the Bloom filter search with cuckoo or XOR in this particular way, but I'd be happy for someone to prove me wrong there. AWS is ripe for abuse like this. You should totally do it. I mean, why not? They're a big faceless company. Abuse them while you can. Somebody once asked me, why didn't you do Graviton ARM CPUs for this? The reason is the compiled binaries were like 20% larger when I tried it. So it meant I needed more lambdas, which meant it wasn't worth it. I need to revisit that at some point. Someone else asked about Lambda layers. CPU's too weak, don't do it. It doesn't really make any difference, and then I'd be paying for storage as well. Defeats the purpose of the idea. It's probably not a good idea to do this at scale. If your thing actually gets popular, this is going to cost you an absolute fortune. That said, I do know that Honeycomb did or used to use something similar to this to search their content in S3, where they would spawn like 1,000 lambdas and then run the query and then return the result. But they're charging like 50 cents a query, which I'm not, so they can get away with it. I think this might be a really good idea for static websites. Maybe somebody wants to explore something like that. And I have a version of the Bloom filter index there if you want to go and have a play with it. Code's there. It's all written in Go, pretty easy to work with. And I was kind of asked, why did you even do this? And I guess I'm slightly patriotic. All of the major search engines in Australia are run by US companies. They're all foreign owned. And I'd love to see an Aussie one, and I'd love to see some investment in this space. Like, it kind of feels ripe for disruption. We've got Kaggy, Marginolia, and all these other niche search engines getting attention. And, you know, we've got the Gen AI, or as I like to say, applied statistics, disrupting all of the larger players. So I kind of feel like now's the time. Somebody, please, do something with this sort of stuff. Thanks for listening. I hope you got something out of this. I'm going to leave you with this comic, which apparently was partly inspired by this experiment. You know, vendor lock-in, they wish. Those vendors are locked in here with me.
Thank you, Ben. We have a couple of minutes for questions. If anyone's got any questions, please raise your hand and I will
perfectly timed.
Anyone? Oh, yes.
Why not link data blobs just with like object files and static data?
Static data. I think I tried something like that, and you end up, like, I think I remember embedding JSON once to try, and then you got to, it didn't work. It was my vague recollection, and then I just went, you know what, I'll just write it out as code. It'll be fine.
Any other questions? Anyone?
Befuddled them all.
Bueller? No? Okay. Thank you.